When Tesla first unveiled its semi-truck 5 years ago, the automotive industry was highly skeptical. Some, like Daimler, even suggested that Tesla might be bending the laws of physics to make it work. Fast forward to today, Mercedes still can't quite figure out how the Tesla Semi is on the road, boasting an impressive 500-mile range. It's clear that there are some magic physics tricks here at play, so why did Daimler doubt the Tesla Semi's feasibility? And how is the Tesla Semi better than most Mercedes diesel monsters? When Daimler was launching its e-Actros test fleet back in 2018, Daimler's head of trucks, Martin Daum, took a dig at Tesla, telling reporters that he had doubts about Tesla's semi-truck. Little did he know that his statements would slowly but surely come to bite him back. When dealing with a guy making rockets and satellites on one hand and, on the other, cars, brain chips, and tunnels, Mercedes should have seen this a mile away. So why did Daimler doubt the Tesla Semi's feasibility? In short, it was a failure of imagination. There were, of course, some obvious ways to boost the truck's efficiency. Tesla focused on improving the Semi's aerodynamics to reduce wind resistance, and they made sure the powertrain used energy efficiently. These changes were expected. However, the less obvious opportunities caught many off guard, like the synergies between the triple cloud motor powertrain and the massive 900 kilowatt-hour battery pack, which Tesla didn't delve into during the Semi's launch event. First and foremost, it's widely known that the semi-truck has a drag coefficient that's nearly half that of a traditional diesel semi-truck, and even surpasses that of a high-performance Bugatti supercar. The drag coefficient measures how efficiently an object moves through the air. Lower resistance equals higher efficiency and consequently more range. However, this metric doesn't consider the volume of air displaced by the object. A larger surface area increases total drag. Let's now explore how the Semi's powertrain is another game changer. In the world of electric vehicles, a typical EV typically achieves around 86% battery-to-wheel efficiency. This means that roughly 5% of the energy is lost in the battery itself due to electrical and chemical inefficiencies. Another 5% is lost when converting DC power from the battery to AC power for motors, and 5% is lost due to motor inefficiencies. In essence, 14% of the energy is dissipated as heat rather than being used to move the vehicle forward. However, when it comes to Tesla and other well-engineered electric vehicles, only 3% is lost in the battery itself, 1% of the conversion from DC to AC power, and 3% in motor inefficiencies. This means that at most, a Tesla achieves an impressive total efficiency of 93% from the battery to the wheels. It's essential to keep in mind that this 93% represents peak efficiency, and the average efficiency likely hovers around 90%. Although a 4% efficiency advantage over a typical electric vehicle might not seem substantial, it makes a significant difference, as we'll see. The Tesla Semi's success extends beyond aerodynamics and advanced electronics. One intriguing aspect is how it leverages its larger battery pack and triple motor setup. At the initial Tesla Semi unveiling, the plan was for the truck to have 4 motors. However, in the production version, it utilizes only 3 motors. This change allowed Tesla to shed weight from the vehicle, ultimately boosting range and efficiency. But how was Tesla able to make this alteration? The answer lies in Tesla's Plaid motor, introduced in 2021 alongside the latest version of Tesla's Model S sedan. Unlike traditional motors that use a steel jack to secure the rotor, the Plaid motor employs carbon fiber. This innovation enables the Plaid motor to operate at higher revolutions per minute before the rotor at the motor's center becomes problematic, resulting in higher power density. In addition to the Plaid motor's carbon fiber wrap, there's another key advantage. It reduces parasitic magnetic fields at high RPM compared to motors with steel sleeves. This innovation potentially enhances power output. The Plaid motor, as a result, delivers roughly 35% more power at high RPM and maintains that power up to 20,000 RPM with high efficiency. This feature enabled Tesla to reduce the number of motors in the Tesla Semi from 4 to 3. The Plaid motor is geared for high RPM, heavy load applications, ideal for the Tesla Semi. For instance, in the Plaid Model S, these motors help propel a 2-ton sedan from 0 to 60 in a breathtaking 2 seconds, with a top speed of over 200 miles per hour. For the Tesla Semi, these same motors are geared to accelerate a 40-ton truck from 0 to 60 in 20 seconds, with an expected top speed of around 85 miles per hour. Interestingly, Tesla could have made do with just 2 or even 1 motor for the Semi and still achieved similar acceleration as a diesel Semi from 0 to 60. For example, the Volvo VN uses 2 electric motors producing 400 kilowatts of power, roughly half the power of the Tesla Semi. However, the Volvo necessitates a 2-speed transmission, whereas the Tesla Semi operates smoothly with a single gear thanks to its powerful motors and high RPM limit, which can easily take it up to 85 miles per hour. So why did Tesla put 3 motors in the Semi when they weren't necessary for keeping up with the power of a diesel Semi? Once again, it all comes down to efficiency. Using 3 motors allows Tesla to optimize one specifically for cruising speed. This in turn enables the other 2 motors, which are geared for acceleration, to disengage during cruising. A similar approach was seen in the older Tesla Model S, where adding an electric motor improved the dual-motor Model S's range by more than 11% over the single-motor version. They optimized one motor for acceleration and another for highway cruising, maximizing efficiency across different driving conditions. Now, there is another critical factor that Mercedes may not have accounted for while spewing doubts about the Tesla Semi regenerative braking. The Tesla Semi can recapture more energy compared to typical Tesla vehicles. To grasp this, let's take a closer look at the Tesla Model 3. An all-wheel drive Tesla Model 3 can regenerate about 70 kilowatts of power with its 2 electric motors. Of course, considering that the Tesla Semi weighs 20 times as much, it needs to recapture at least an order of magnitude more power. So what's the limiting factor here, and how is Tesla able to overcome it? In the case of the Model 3, the regen limit of roughly 70 kilowatts is primarily a software-imposed restriction. This software limit is likely in place to maximize the battery's lifespan. However, performance Model 3s with similar motors and battery packs can regenerate up to 100 kilowatts when in track mode. These vehicles have a higher profit margin, and Tesla can absorb the potential warranty claims from intense track usage. Some might argue that the 70 to 100 kilowatt regen limit can't be due to battery constraints, because a Model 3 can accept up to 250 kilowatts of power on a Tesla supercharger. But there's a catch. This high charge rate is only possible when the battery is nearly empty and has gone through a specific conditioning process to enhance charge acceptance. Even then, it takes a minute or two for the battery to ramp up from 100 kilowatts to 250 kilowatts, which is not feasible under spontaneous braking loads. If this assumption is correct and the battery is the limiting factor for regenerative braking, then a larger battery pack with a more extensive energy reservoir should enable the capture of more energy during each braking event. The Tesla Semi's battery pack offers around 900 kilowatt hours of usable energy storage, which is more than 11 times the energy stored in a Model 3's 78.5 kilowatt hour battery pack. This means that instead of accepting just 70 kilowatts of regen power like the Model 3 battery pack, the Tesla Semi's battery pack should comfortably handle around 770 kilowatts of regen power. This immense capacity allows the Semi to recapture energy at an impressive rate during braking, contributing once more to its outstanding efficiency. This means the Tesla Semi can efficiently harvest every bit of kinetic energy while descending hills and applying the brakes, converting it into chemical energy stored in the battery instead of wasting it as thermal energy. Consequently, the 500-mile range version of the Semi might enjoy efficiency advantages over other semi-trucks in the market, sporting smaller battery packs. The larger battery pack and triple motors allow the Semi to absorb every ounce of energy during demanding downhill journeys that could overwhelm a smaller battery pack. Lastly, it's worth noting that the Tesla Semi transitioned from Tesla's typical 400 to 500-volt architecture to a more advanced 1000-volt architecture. This upgrade does offer efficiency benefits, but the extent of these benefits depends on how Tesla leveraged the higher voltage. Increasing voltage in an electric architecture can be leveraged in several ways, such as reducing wire thickness to cut costs, increasing power output, or enhancing efficiency by minimizing heat generation. The move to a 1000-volt architecture could have brought a range of improvements, further optimizing the Semi's performance and efficiency. The Tesla Semi represents a remarkable convergence of innovation, efficiency, and engineering prowess. Its triple-motor setup, advanced plate powertrain, and substantial battery pack enable exceptional acceleration and unprecedented regenerative braking capabilities. This means that every downhill descent becomes an opportunity to recharge the battery, granting the 500-mile range version of the Semi a notable edge in energy efficiency over competitors with smaller battery packs, and another chance to prove Mercedes wrong. And that's all from this video. What do you think about the Tesla Semi? Remember to like and subscribe so that we can always update you with everything happening in the automotive world. See you in the next one.